Hey guys, today we're going to learn how to evaluate for trigonometric limits. Now we have done some trigonometric limits in the past using only direct substitution. So let's practice that. For this first one, we have the limit as theta approaches pi over 6 of -2 sine of 7 theta. Remember that all of this represents the angle. So let's plug in the pi over 6. That would give us -2 sine of 7 pi over 6 when we multiply the pi over 6 with 7. If we look at the unit circle, we have -2. The sine of 7 pi over 6 would be -1/2. So -2 times -1/2, these would cancel along with the negatives, and that would give me an answer of 1. For this next one here, we have the limit as theta approaches pi of 4 cosine squared theta. Now, just so you understand what cosine squared is, cosine squared is the same thing as saying cosine of theta squared, where everything is being squared. So that's just saying that we have two cosines, cosine theta times cosine theta. So if you have the little squared right after the trig function, it means that the entire thing is being squared. This is not the same as saying this. If the squared is after the angle, that means that only the angle is being squared. So keep that in mind in the future. Now, let's go ahead and work this one out. So we're going to plug in the pi. So this would be 4 cosine of pi, and all of that gets squared. The cosine of pi, if you look at your unit circle, right, pi is over here, and this is the coordinate -1, 0. So the cosine of pi is -1. So this is 4 times -1 squared, which is 4 times 1, leaving us with an answer of 4. Last one here, we have the limit as theta is approaching 0 of 1 minus cosine theta over sine squared theta. So let's plug in 0. We would get 1 minus cosine of 0 over sine of 0 squared. Now here's 0. This is the coordinate 1, 0. So remember, the x is cosine, the y is sine. So 1 minus the cosine of 0, which is 1, all over the sine of 0, which is 0 squared. This leaves me with 0 over 0. Now this does not necessarily mean DNE. This is indeterminate. Indeterminate because we cannot determine what this limit is. Reason why we get 0 over 0 means that there must be some sort of common factor in the numerator and the denominator that will cancel out. So what we are going to do now to try to evaluate for this limit is we're going to see if we can rewrite this expression here in a way that if I were to plug in 0, I would get an actual answer. Now how we do that is by using the Pythagorean identities. These are my identities. We have sine squared plus cosine squared is equal to 1. 1 plus tangent squared is equal to secant squared. And 1 plus cotangent squared is equal to cosecant squared. This first one here is the most commonly used Pythagorean identity. Sine squared plus cosine squared is equal to 1. So let's see how we can use this Pythagorean identity to rewrite this limit so that I can actually find an answer. Now, how do you know if you're going to use a Pythagorean identity? Typically, if when you try direct substitution first and it does not work, if you have something that is squared, we may be able to use one of these identities. Since if you look at all of these trig functions, they are all squared. So let's see how we can do that. In the numerator, we're going to leave it as 1 minus cosine theta, since this is not squared. However, the denominator, sine squared, I'm going to see if I can apply a Pythagorean identity. This is my Pythagorean identity that has sine squared. It's the only one, so this is the one I'm going to have to use. I'm just going to copy the identity first so you can see what I'm going to do. I want to see if I can replace sine squared with something else. So this identity allows me to solve for sine squared. So I'm going to subtract cosine squared to both sides. This leaves me with sine squared is equal to 1 minus cosine squared. So I can take the sine squared, right, because that's what this is, and replace it with this. So let's rewrite that function so far. We have 1 minus cosine theta over 1 minus cosine squared theta. Now this 1 minus cosine squared, it may be hard for you to see, but this is a difference of squares. And how I know this is because, first of all, it's a difference. We have subtraction. 1 is a perfect square because if I square root 1, I get 1. And cosine squared is also a perfect square. Remember that I can rewrite cosine squared as cosine theta squared. So if I square root that, the square root will cancel out with the exponent, and that will give me cosine theta. So that is also a perfect square. So keep in mind how we write perfect squares. We square root the first term, 1. We square root the second term, cosine theta. Make one factor positive, one factor negative. So in the numerator, I have 1 minus cosine theta, and the denominator would be 1 plus cosine theta, 1 minus cosine theta. See, I have my terms square rooted. I made one factor positive, one factor negative. And now what happens is I can cancel out these 1 minus cosine squared. So let's rewrite this limit so you can see how we're going to evaluate it. This is the limit as theta approaches 0. There's nothing left in the numerator, so we're going to write a 1 over 1 plus cosine theta. Now we can plug in the 0. This will give me 1 over 1 plus the cosine of 0, which again, if you look at your unit circle, is 1. So we end up with a final answer of 1 over 1 plus 1, which is 2. So 1/2. Let's try this other one. We have 3 cosine squared theta over 2 minus 2 sine theta. So again, if you try direct substitution first, if you take that pi over 2, we would end up with 0 in the denominator, meaning let's try something else to see if we can rewrite this and be able to solve for that limit. So cosine squared. This means I can use a Pythagorean identity. Again, I'm just going to rewrite the identity as is. Sine squared plus cosine squared is equal to 1. I want to replace cosine squared, so I'm going to solve for cosine squared here by subtracting sine squared on both sides. This means that cosine squared is equal to 1 minus sine squared. So that's what I'm going to replace up here. So let's rewrite this. This would be 3 times 1 minus sine squared theta over, in the denominator, these two terms have a 2 in common, so we can take out a 2, and that will leave me with 1 minus sine theta. Now, just like in the previous example here, where we can factor 1 minus cosine squared into a difference of squares, it's the same thing here. 1 minus sine squared is a difference of squares. So I can rewrite this as 3 times 1 plus sine theta times 1 minus sine theta, all over 2 times 1 minus sine theta. These factors here would cancel, and so let me rewrite this limit. This is the limit as theta approaches pi over 2 of 3 times 1 plus sine theta all over 2. Now we can plug in the pi over 2. So we get 3 times 1 plus the sine of pi over 2. Pi over 2 is up here. This is the coordinate 0, 1. So the sine of pi over 2 is 1 all over 2. This is 3 times 2, so 6 divided by 2, which is equal to our final answer of 3. Now let's look at some other identities that we can use. These are called the reciprocal identities, which we have used very briefly in the past. We have cosecant, which is the reciprocal of sine and can be written as 1 over sine. We have secant, which is the reciprocal of cosine, which can be written as 1 over cosine. And cotangent, which is the reciprocal of tangent and can be written as 1 over tangent, or cosine over sine, since the reciprocal of tangent, which is sine over cosine, would give you that cosine over sine. So let's look at this limit. We have here the limit as theta approaches pi of sine of theta over over tangent of theta. If you were to plug in pi, we would end up with 0 in the denominator. Remember that you always want to check if direct substitution will work first, and if it doesn't, then we would go ahead and apply some properties. Because direct substitution would not work, let's rewrite this in terms of sine and cosine. Usually, that's the first thing I try, is rewriting all of our trig functions so that we only see sine and cosine. So the numerator is just sine. Tangent can be written as sine divided by cosine. So when we have it written like this is like we're saying sine of theta over 1. I'm just going to put it over 1 because it's not a fraction, over sine of theta over cosine theta. When you're dividing fractions, remember that we are multiplying by the reciprocal, or copy, change, flip. So I'm going to copy this first one, sine of theta over 1, times the reciprocal of the denominator, which would be cosine theta over sine theta. By writing it like this, remember anything that is diagonally across that are the same can cancel. So the sine of theta will cancel, and we're left with cosine theta over 1, which is just cosine theta. So this is my new limit. We are going to evaluate for the limit as theta approaches pi of cosine of theta. So now we're going to plug in the pi. Pi is over here, which is the coordinate -1, 0. So the cosine of pi is equal to -1, and that would be my answer. Let's try a couple of those. For this first one, we have the limit as theta approaches 3 pi over 2 of tangent theta cosine theta. So again, we're going to first try to rewrite things in terms of sine and cosine and see what happens. Tangent is sine divided by cosine. And now we're going to multiply with cosine, which is just over 1. The cosines here cancel. And all that's left is sine of theta over 1, which is sine theta. So this is my new limit. We are trying to solve for the limit as theta approaches 3 pi over 2 of sine theta. Plug in the 3 pi over 2, we get the sine of 3 pi over 2, which on my unit circle, 3 pi over 2 is down here, which is the coordinate 0, -1. So the sine is equal to -1. Let's look at this next one here. We have the limit as theta approaches pi of cosine theta tangent theta over sine theta. Let's rewrite this in terms of sine and cosine only. In the numerator, we have cosine theta times tangent, which is sine theta, over cosine theta. divided by sine of theta. Now this is just over 1. Here, my cosines will cancel. So in the numerator, I'm left with sine of theta over 1, which is just sine theta. And in the denominator, I have sine theta. And sine over sine is going to equal to 1 since they're going to cancel. Now, this is my new limit. The limit as theta approaches pi of 1 is going to equal to 1. And this is because if you remember when we were looking at properties of limits, the limit as x approaches a of any constant is going to equal to the constant. So this is a constant. So it doesn't matter what theta or x is approaching, the y value will always just be that constant, that in this case 1. Last one here, we have the limit as theta approaches pi over 4 of secant theta minus tangent theta sine theta. So we're going to rewrite everything in terms of sine and cosine. Secant is 1 over cosine theta minus tangent, which is sine theta over cosine theta times sine theta, which I'm going to put it over 1. So now let's rewrite this. I know it looks messier than the original one, but you're going to see what's going to happen now. This is 1 minus sine times sine is sine squared theta. And everything is over cosine, as you can see here. Let me just break it up so you can see. This is 1 over cosine theta minus sine squared over cosine theta. Since they're both over cosine theta, we can turn this into 1 fractions because they have the same denominator. So this is 1 minus sine squared all over cosine. Now 1 minus sine squared should look familiar. If I look back at my identities, I even have it boxed here. 1 minus sine squared is equal to that cosine squared. So what I could do there is I could take this 1 minus sine squared and replace it with cosine squared over cosine theta. Now again, remember, cosine squared is the same thing as saying cosine theta times itself all over cosine. This is going to cancel one of those cosines. So this is my new limit. The limit as theta approaches pi over 4, all that's left is cosine theta over 1, which is just cosine theta. And the cosine of pi over 4 is the square root of 2 over 2. Now, let's have a look at a couple of other trigonometric limits. There's something called a special limit. And before I introduce what those special limits are, we're going to look at all of these equations and their graphs and evaluate the limits for as x is approaching 0. So this first function is sine of x over x. And as x is approaching 0, this limit would be 1. For sine of 4x over x, the limit as x approaches 0 is 4. And last one here on the top, we have f of x is equal to sine of 6x over negative 3x. And if you try to find the limit for as x is approaching 0, that would be negative 2. Now let's look at these bottom row functions, which are all with cosine. We have 1 minus cosine 4x over negative x. And the limit as x is approaching 0 of this function is 0. For this one here, f of x is equal to 1 minus cosine 5x over 2x. The limit as x is approaching 0 is 0. And this last one here, 1 minus cosine x over x, the limit as x is approaching 0 is 0. So what are these special limits? For the first one, we have the limit as theta is approaching 0 of sine of c theta over c theta is going to equal to 1. So now c is just any number, a constant. Okay, typically if they are the same number, then the answer would be 1. The limit as theta approaches 0 of 1 minus cosine c theta over c theta is going to equal to 0. And the limit as theta approaches 0 of tangent of c theta over c theta is also equal to 1. So first thing, before we can apply these special limits, these are only valid for as theta is approaching 0. So if theta is approaching any other number, these special limits do not apply. Now this first one and this last one have the same format, sine and tangent. It's the same formatting, except one has sine and one has tangent, but the answer is 1. And then finally we have the 1 minus cosine, so the one that, this last one here is 0. Now, all of these limits apply as long as theta is approaching 0, as I mentioned, but so do their reciprocals. So if this was written c theta over sine of c theta, it would still equal to 1. If this was c theta over 1 minus cosine of c theta, it would also equal to 0. And if you had this last one here as c theta over tangent of c theta, it would still equal to 1. So keep that in mind. Now, our shortcuts. These are the limits that we were finding using the graphs. We can use our special limit properties here and not need the graph, and not need to even plug anything in. So the limit as x is approaching 0, look at what we have here. This is our special limit, c over c theta, right? The trick is just look at the numbers. Sine of 4x over x. Whatever the numbers are, that's what you're going to divide. So the sine of x over x is 1, and whatever numbers are left over, that's part of our limit. So we have the 4 in the numerator over, this is 1, 4 divided by 1 is 4. And if you look back at that limit, you see how we got there from the graph as 4. Now this is the formatting of this special limit, 1 minus cosine of 5x over 2x. Here we don't need to divide those numbers because this particular limit is going to always equal to 0. And this last one here, we have the sine of 6x over negative 3x. We take those numbers, we have 6, negative 3, and we divide. 6 divided by negative 3 is equal to negative 2. And this would be the answer to that limit. And that is this graph over here. And you see how we got negative 2 from the graph. So now let's put all of this together. Notice that these are all limits for as theta is approaching 0. So if you need to, or if you can, we would apply those special limit properties. So with this first one, we have 2 sine of 5 theta divided by 3 theta. So this is that format of that first special limit. And we're going to take those numbers. We have the 2 and the 5. They're both in the numerator, so we're going to multiply over the 3. 2 times 5 is 10 over 3. And this would be my answer to that limit. Now this one here, we have 1 minus cosine theta over theta plus 2 sine theta over theta. Sorry, I said over theta twice, but basically everything is being divided by theta. But what happens here is that this looks to be like almost 2 of the special limits combined. So just so you can understand how we can apply our special limits here, what we can do here is split the fraction. You know how if you had 1 over 2 plus 3 over 2, everything is over 2, right? So we would just add the numerators, 1 plus 3, and leave it over 2. That's what happened here. This is 1 minus cosine theta plus 2 sine theta, and everything is over theta. So I'm going to, instead of putting it together like I did here, I'm going to split it back up like it was originally. So this would be 1 minus cosine theta over theta plus 2 sine theta over theta. This means the same thing because if we're adding, the denominators don't change, but we would add the numerators, which would give me this original limit here. Now, according to our special limits, this is equal to 0, plus this, which is equal to 2. And 0 plus 2 is 2. Over here, we have the limit as theta approaches 0 of theta times cotangent theta. Now, if I'm going to use my special limits only use sine, cosine, and tangent. So this cotangent, right, I know that this is the reciprocal of tangent. So this is the same thing as saying theta times 1 over tangent theta, which is equal to theta over tangent theta if I actually multiply this out. This is a special limit. If I look back, remember what I said, that the reciprocals also are the same. So tangent of theta over theta, the reciprocal is theta over tangent theta, and that is going to equal to 1. Now let's say you didn't recognize this, but you wrote this in terms of sine and cosine. This would be theta times cosine theta over sine theta. If I just rearrange my multiplication here, this is theta times cosine theta all over sine theta. This is a special limit, which equals to 1, times cosine of 0, which is 1, and 1 times 1 still gives me the same answer of 1. Last one here, we have the limit as theta approaches 0 of sine theta minus sine theta cosine theta all over theta squared. Now, the first thing I notice in the numerator is that both terms have a sine theta, so we can factor out one of those signs, and that will give me 1 minus cosine theta, and everything is over theta squared. Now the reason I'm doing this is so that way maybe I can see if I can spot any of my special limits here. Now let me just rewrite this a second so you can see where I'm going. The numerator I'm going to keep as sine theta times 1 minus cosine theta. And theta squared is basically saying theta times theta. So again here, I can still split this fraction. But this time it's not the same as addition, where everything is over the same denominator. When we multiply fractions, you multiply straight across. So let me show you. This is the same thing as saying sine of theta over theta times 1 minus cosine theta over theta. See how I had split up the theta squared into two different thetas, and then I split them here. Because when we multiply fractions, we multiply numerator with numerator. So sine theta times 1 minus cosine theta, that gives me the numerator. And then the denominator would be theta times theta, which gives me that theta squared. And these are my special limits. Sine theta over theta is 1, and 1 minus cosine theta over theta is 0. And 1 times 0 gives me 0. And that's limits of trigonometric functions.